Today we're moving on to Unit 6, where we talk about periodic functions or trigonometric functions. So in Unit 5 we learned a lot of trigonometry, what happens when you do sine, cosine, tan after 90 degrees, what kind of interesting situations does this create. To this unit we're more looking at the function sine x, like as a function, as a graph, as opposed to something we would use to solve a triangle. Now, the first thing to understand in this unit is the idea of something being periodic. And I'm going to give you the mathematical definition for periodic right here. And I like to start with this because it's confusing, but not. So a periodic function is one such that f of x is equal to f of x plus t for all values of x. If you can come to explain this to me, you will understand what a periodic function is. Let's look at this function here. This function is periodic. So this what I give you here is the mathematical definition. This is how you describe it in math. How would you describe it using language? A function whose values repeat. So it goes up, and then down, and then up, and then down, and then up, and then down. It just repeats over and over again. Now my definition says that if you take any point x, so let's draw this first of all. Let's draw a curve that looks kind of like this. So we'll make it sine x plus 3. That looks, I guess, sine x plus 2 is closer to what they had. We'll come back to why it looks like this later, but here's a point. Okay? Now, what I'm saying, my definition is, if you were to draw another point, if you were to take another point that was exactly a certain distance away, you would have the same y value. And if you notice, no matter where I put this point, if I move exactly t units away, it has the same value. That's why the mathematical definition of periodic works. Because if you draw a point, and then you draw a second point t units to the right or t units to the left, it doesn't matter, you would be at the same y value. And remember, the y value is f of x. So the y value at 1, let's say, would be the same as the y value, at, it looks like they're, at 1, we're over here, maybe at 4, or a little past 4 maybe, right? It's hard to tell from this chart. But anyway, that's what periodic means. It means whatever the y values do in a certain interval, they just keep doing that over and over again. Okay? So let's look at this graph now and analyze a couple of things about periodic behavior. What does it sort of do, and how do we express it? So it says, does this graph model periodic behavior? The answer is yes, because the graph continues patterns of y values every 4. Again, it's kind of hard to tell. Let's say every 3. Sorry, every 3 every 3 x. So since it takes 3x to, let's say a distance of x equals 3 to repeat the function's pattern, we say the period is 3. So the period is how much time, or how much x value, let's say, does it take to repeat. So here you can see that if I start here, I go up, then down, and then I'm back right where I started, right at 3. and then I go up and down, and I'm right back where I started at 6, and then up and down, and I'm right back where I started at 9. So every 3 x's, I repeat one cycle, and that's what it says here. The period is the sort of time. It's not always time, that's why it's in quotation marks, but it's kind of like the x distance that it takes for the graph to do one cycle. Now, these graphs, when you have a wave, okay, that's what this pattern is, right? It's a sinusoidal wave is what we call it. It has an axis. Now, it doesn't really have an axis the way a parabola has an axis. If you remember, a parabola had an axis that was vertical. This type of graph has a horizontal axis that kind of runs through the center of the picture. So here, if I draw the line y equals 2, and let's just hide what I had before. Y equals 2 is what we call the axis. You can kind of think of it as like half of the graph is above it and half of the graph is below it. Okay, so the equation of the axis is a horizontal line that's halfway between the max and the min, and here's the first equation for you to understand. The equation of the axis is y equals, because it's a horizontal line, so y equals, since it is a horizontal line, and then the value that y is equal to is the max plus the min, max plus min divided by 2. I don't know why it's doing that. Divided by 2. Oh boy. Okay, so that's how you find the axis. So like if we go back up to this one, the minimum is 1.6, the maximum is 2.4. 2.4 plus 1.6 is 4, divided by 2 is 2, and I draw this line straight across at 2, right? So it would look, you know, on yours if you have it on paper. Yeah, it won't let me draw a shape on another shape, but try it here, I guess. Yeah, it just look like that, right? It's a straight horizontal line at y equals 2. All right, now the amplitude, okay? The amplitude is the distance between the axis and the max or the min, right? So like, if I go back to my chart for a sec, and I draw a point at, let's just see, where would this be? There, and then vector 0, 1, and then vector b plus v. Okay, so just forget about all of how I did all that. It doesn't matter for what we're doing right now. This here is the amplitude. Okay, so just draw a pointer to it. Oh my goodness. Okay. Amplitude equals distance from axis to max. Now, you could just as easily draw an amplitude going here, like going downward, where it would be the distance from, so let's go, okay, let me just see if I can do this in my head. So it would be 2, and then it would be negative w plus 3 pi over 2, 2. Okay, so there we go. So that's also an amplitude. So let's just quickly make that point as well. So let's hide the label for that, and then from axis to max or axis to min. Both of these, of course, are the same because we know that the axis is halfway between the min and the max. So that one would be an amplitude, and this one would be an amplitude. In this case, they're both equal to 1. It doesn't matter that it points up or down because it's a distance. It's always a positive number. Okay, so the distance between the max and the min. So just to solve the amplitude, you do A equals max minus min divided by 2 this time. Okay, so max minus min. So again, the axis was max plus min divided by 2. The amplitude will be max minus min divided by 2. In our case, that would be, right, the max was 2.4, the min was 1.6, and then we divide by 2, so we get 0.8 divided by 2, which is 0.4. And that would be the amplitude of this picture. Between 2 and 2.4, of course, it goes up by 0.4. What is the range of this function? Now, periodic functions have a range of, okay, well, at least let's just clarify this, sinusoidal periodic functions, because some periodic functions don't have this, but the waves that were there, so this one we're looking at is called a sinusoidal wave. So if you're looking at a sinusoidal wave, which the vast majority of the time you are, you can use this equation. They have a range, very, very straightforward. Y is in the real numbers such that the min is less than equal to y is less than equal to the max. Okay, so really straightforward. So in our case, we would say y is in real numbers, and 1.6 is less than or equal to y, which is less than or equal to 2.4. Okay, and that's it. Pretty straightforward. When is the graph at its highest point and lowest point? Okay, I want to again make an important point to you here. Obviously, you can just look at this and you can go, okay, it's at its highest point at 0.75. So highest is 0.75 and 2.4. Lowest is 2.25 and 1.6. I want you to focus, though, rather than on those specific numbers. So here's, 2.25 there. I want you to focus on this idea. 1/4 of the way through the period, it is at its highest point. Remember that the period was 3, so 1/4 of 3 is 0.75. That's where I got that from. It's at the lowest 3/4 of the way through the period. Now, it's not that this is always true, but I want you to think about it this way. It's not just 0.75 and 2.25, like those numbers are important. The importance is it's always a certain fraction of the period that these functions go to their mins and maxes, and we will look at this in a lot more detail later. I just want you to start thinking about it this way. So if we were to think of this function, let me just see. Yeah, all right. So let's look at sine. What does sine x look like when you graph it? Okay. Now sine x, when you put in sine 0, you get 0. When you put in sine 30, you get 0.5. When you put in sine 60, we know from our triangle that this is root 3 over 2, but as a decimal, it kind of approximates to 0.866, right? So if you go like sine 60 degrees, you get 0.866. So that's where I'm getting that from. Sine of 90 is 1. Sine of 120, well, 120 has the same beta as 60, right? So like let's put 120. Let's actually, you know what? Let's do this for all of them. Let's for all the ones with the same beta. So here, 60 has the same beta as 120, which has the same beta as 300, and the same beta as 240. All of those have the same beta. We did this one at last unit. And if you remember, the numbers were, or you can just use your calculator for this, 0.866, then negative 0.866, and negative 0.866 again. Okay, I'm going to just drop the font size a little bit here to see if I can get these to fit on one line. Make this a little bit. Where's the button for font? Just condense it a bit. Okay, there we go. Now, 30, right? Let's analyze ones with a beta of 30. 30 has the same beta as 150. It has the same beta as 210. And it has the same beta as 330. all of those angles are 30 degrees away from the x-axis. Therefore, they all must have a value of 0.5, but we know that the ones in quadrant 3 and 4 are negative. Sine of 180 is 0, sine of 270 is negative 1 if you try on your calculator, and sine of 360 is 0. So these are the values that you get, okay, when you do sine of these various numbers. Now let's make a new graph here, and obviously I'm going to need to really shrink this x-axis down if I want to get to all those values. But let's graph them. So we had 0, 0. We had 30 and 0.5. We had 60 and 0.866. We had 90 and 1. Now, by the way, you have this space to be doing this, so, I think if you count by 30s, you should be good here, because 1, 2, 3, 1, 2, yeah, to count by 30s is good, and then you can just plot the points with me as we go, right? So it says increments of 30. All right, so then, okay, so let's keep going. So at 120, we knew it was 0.866. At 150, it was at 0.5, and at 180, it's at 0. Okay? At 210, it was at negative 0.5. At 240, it was negative 0.866. At 270, it was negative 1. At 300, it was negative 0.866. At 330, it was negative 0.5. And at 360, it was back to 0. So this is what you should have on your page. Something obviously not without the A, B, C, D, and so on, but okay, so you should have all those points. Now, when I graph the sine x function, sine x, that's what it does. Okay? It just repeats that pattern over and over and over. And of course, why it repeats that pattern over and over and over again is because if I ask you to draw let's say I asked you to draw a 400-degree angle. Okay? So, again, maybe a new window would be better for this. Let's draw a 400-degree angle. So here's 1, 0, here's 0, 0, and then we're going to say, let's make a slider that goes from 0 to 400. Okay, and then let's say point C or point P equals rotate point A alpha degrees around point B. Okay, so take note, here's a 60-degree angle. Okay, so again, let's just see remember what I'm talking about. A, B, P. Okay, so there's a 60-degree angle. Now, maybe just for the sake of it, let's call a point angle 60 equals rotate a 60 degrees. Okay, so there's where a 60-degree angle is, just for your reference. Let's make a 400-degree angle. I should have done my math better because it wasn't. It's not 400 I'm thinking of, it's 420. Let's make a 420-degree angle. Okay, 420-degree angle and a 60-degree angle are exactly the same. It's like saying, picture two friends. You tell one of them to turn 60 degrees to their right. You tell the other one, spin around 360 and then turn 60 degrees to your right. Both people would be facing the same way because spinning around 360 just gets you exactly back to where you started. So if you do another 60 after that, you would look at the exact same place, right, that a person who just went the original 60 would be going. So a 420-degree angle is the same thing as a 60-degree angle in every mathematical way. It just means you spun around the circle once. And for the same reason, we could take this same equation and say it is also the same as a 780-degree angle. Right? So let's open up my thing here so it can go up to 800. Or 8,000, I guess is a little overkill. 800 is good. Okay? If you take this up to 780, right? Again, I'm in the exact same spot because all I've done is just go around the circle in a repetitive way. Now, when you look at the sine graph and you ask what would the graph be doing at 400, well, it would be doing the exact same thing it was doing at 40. What is it doing at 450? The exact same thing it was doing at 90. Let's just see, I can make this a little bit easier to make it look like yours if we count by 30s, right? So look at 450. You're at the maximum. Look at 90. You're at the maximum. 90 to 450 is exactly 360 degrees apart, which is why we say sine has a period of 360 degrees. Because it takes 360 degrees for sine to complete its cycle, and then it starts over again. And that should make sense because rotating around the circle, it takes 360 to do a rotation, right? Let's talk about sine. The period of sine is 360 degrees. The maximum value is a 1. The minimum value is a -1. The amplitude is a 1. Because if you look at my picture here, and you think about the axis, which in our case is y equals 0, you can go up 1 or you can go down 1. You can't get any farther away than that. Okay, the x-intercepts. There's an x-intercept at 0, at 180, and at 360, right? At 0, 180, and 360. So there are 3 x-intercepts for one cycle. The y-intercept is just 0, 0. The domain is x is in any real number. You can do any real number into this and it will work fine. As you can see, there is no limitation to x because x can go as far as you want to the right or as far as you want to the left. The idea would be any angle is possible. A 1,000 degree angle is possible, but a certain amount of it would be wasted time because you're just going around in circles, right? You're just going around the circle 3 times. The range, though, is limited. The y is in real numbers, but it has to be between -1 and 1. This is why, this is another reason, when you try to inverse sine a number like 1.25, you're going to get an error. Because sine never reaches 1.25, it never goes higher than 1, and it never goes lower than -1. So this is why you can get an error when you do the inverse sine button, right? If you try a number bigger than 1 in there. Okay? Now, I just want to quickly check this. So we're doing cos, and that's it. And is tomorrow the, like, it's how to draw... I'm sorry, I shouldn't ask you to watch me scroll through this, but I just want to look for... I don't think this is actually anywhere in the picture. So I want to do something for you that I think you'll find valuable, but I'm going to do it at the end of the lesson. So let's go back and do cos. Now cos, okay, works a bit different than sine, but like sine, we also can take advantage of the fact that we know how the beta works with cos, and that all the ones with the same beta would have to have the same value. So for example, the blue will all have the same value, and that value is 0.866. Let me just copy these two because I adjusted the font correctly. Okay, so these are not the right answers. I just wanted it to have the right font. Okay, now cos. I know that the cos of 30 from my special triangle is 0.866. I know that the sine... Okay, so that was clearly a waste of time because... sorry. Size 8. Font condensed. Okay. The cos of 60 is 0.5. Now, and the cos of 90 is 0, and the cos of 0 is 100. You may need your calculator to do that one, but you just go on your calculator and you go cos 0, and you get 1. So okay, so cos of, so you get 1. Now, every one that's blue has to be the same as 0.866, except 150 is in the second quadrant where cos is negative. 210 is also in a quadrant where cos is negative. 330 is in a quadrant, where cos is positive, so I put the positive there. Okay, now for the red ones, 0.5, I know cos is negative in quadrant 2, negative in quadrant 3, but positive in quadrant 4. This just leaves me with filling out the rest of it. Cos is 180 at is negative 1 at 180. Again, you can just check this for yourself. Cos of 180 degrees is negative 1. It's 0 at 270, and it's back to 1 at 360. Now again, let's draw it together. So I'm going to just, I guess, yeah, I guess we don't need this. Let's go back to this one. So again, I'm going to delete all these points. We'll get rid of sine. We'll get rid of this. And you just draw with me as we go through cos based on our table here. Okay, so our first point was 0, 1. Our second point was 30 and 0.866. Then we had 60 and 0.5. Then we had 90 and 0. Okay, then we had 120 and negative 0.5, 150 and negative 0.866, 180 and negative 1. Then we had 210 and negative 0.866, 240 and negative 0.5, 270 and 0. And then we had 300 and 0.5, 330 and 0.866, and finally 360 and 1. Now, cos, when you first look at it, it may not be as obvious that the pattern is actually the same as sine. Let's draw cos. Oops. So here, just to clarify what just happened. When you type cos x in GeoGebra, it probably thinks you meant using a different type of angle system. So you need to say cos, I don't know if it does cos, no, it doesn't work that way. So you need to say cos x degrees. Now, to make degrees, okay, so let me get rid of cos x so to make degrees, okay, you can use this little thing in the bottom where this is like all your symbols, and you just click degrees. It just goes right there. Okay. If otherwise, I think your phones you can get to degrees somewhere using your keyboard. If you have a Windows computer, you can make the degree sign. I'll just write it here. Maybe we can. I'll just put it over here. To make the degree sign on your computer, type or hold Alt and then press 0176 on your numpad. Okay, so if I hold Alt and press 0176, it produces that little degree sign. Anyway, cos x degrees, as you can see, is the same wave as sine. So in many ways it's the same wave, but instead of starting on the axis, which sine did, okay, so here's in red I have sine, in green I have cos. So it's the same wave, okay, it's just it starts in a different place. So cos starts at its maximum, whereas cos starts at its maximum and is on the way down, whereas sine starts at the axis and it's on its way up. Okay, and that's really the difference between the two. So again, I'll let you draw that here. The period is still the same. It takes 360 to repeat. The maximum is 1. The minimum is -1. The amplitude is 1. The intercepts this time were at 90 and 270, right? Those were the two places where cos x went through the x-axis. So here at 90 and there at 270. It has a y-intercept of 0, 1. It has a domain of x is in the real numbers, and it has a range, the exact same range as sine. Y is in the real numbers such that -1 is less than or equal to y, which is less than or equal to 1. Okay? And that's the same for sine and cos. So they are congruent curves. The cosine curve is the sine curve translated 90 degrees to the left. That is true. Kind of creates an interesting little identity that we didn't talk about, which is that cos x equals sine 90 minus x, right? It's kind of an interesting identity. I don't think we're going to need to use it, but just so you can see. It also equals sine x plus 90 as well, right? Because it says the sine curve translated 90 to the left. So how would you translate 90 to the left? You'd have a d value, and you'd say plus, because you want it to move left, and you go x plus 90. Right? So if I draw sine x plus 90, oops, x degrees plus 90 degrees, I get cos, right? I get the same thing. Okay, so one quick last thing I just want to show, which is another way of understanding how this equation comes from the value of sine. So if you remember when we drew the unit circle, so circle 0, 1, we're going to have a point A, which is 1, 0, and then we're going to have an origin, and then we're going to have a point, which is, and let's make a slider here where we can rotate an angle, let's say between negative 720 and positive 720. Okay, and I'm going to shrink it down a little bit so that it makes sense, but let's say rotate alpha degrees. Okay, now I'm going to make a point called sine graph, and what I'm going to do is I'm going to use the angle that we're doing divided by 10, I think, so to keep it shorter, and then the y value of the point that I rotated. And I don't want it to be a vector, I want it to be a point, so we'll call it s. Okay? So as I move around the circle, this point that I'm drawing is just going to copy the y value of that one. And I think just to make this probably work a little bit better, let's divide it by 5. Okay? Now watch what happens when you rotate around the circle but track the angle. Okay, so watch. Sine, think about the y values. What are the y values doing? They're at 0. They're rising rapidly. Then they're rising a little more slowly, and they get to their maximum. Then they turn around and they start to drop. And then they start to drop very rapidly. And then the y value is back down to 0. And then I go down, the y value drops below the axis, all the way down to -1, and then the y value comes back to 0. And what happens after that? It just goes around the circle again and provides the exact same pattern. So if you remember, one of the things I asked you to investigate last unit was the idea that the y coordinate on the unit circle equals sine of theta, right? Or whatever, sine of x here. And you can see that if you take those y values and unwrap them, they form a perfect picture of the sine graph. And if I continue to work that graph in a negative direction, I just keep getting the same thing over and over again. I get that same wave as that a value goes around and around the circle. Okay? Let's do the same thing one last time, but this time let's track the x coordinate. Okay, so instead of tracking the y value, I'm going to track the x coordinate. Okay, so first thing to notice, right now with a 0-degree angle, the x coordinate is a 1. So my graph starts at 1. Now as the x coordinate shrinks, so it goes back towards the axis, my graph goes down. Okay, now the x value is going to go all the way over to the left at -1. My graph is going to go down to -1, right? And there's cosine going all the way down to its minimum. Now, the x value of the graph is going to come back to 0, which is what the cosine graph does. Finally, the x value of the graph of the circle is going to go back to 1. And that's indeed what the cos graph does. And so if you just keep stretching this, right, or you go around the circle a couple more times, you just get the cosine graph. Okay, so again, I'll just do it at the simpler dots, but that's the idea. Okay, so the cos graph is what would happen if you mapped all the x coordinates on the unit circle and the angle that went with them. And you would get this wave. And the y coordinates of the unit circle produce the sine graph. Okay, so there you go. So as that angle goes around the circle, right, if we were to track what angle you're at and what x coordinate you're at, you produce the graph of cos x perfectly. Okay, and this is the connection between what we were doing last unit and what we're doing now. We said in last unit cos was negative in quadrants 2 and 3. Well, look where I am in quadrant 2 and 3. Right? As soon as I enter into quadrant 2, I'm down here on the graph where it's negative. As soon as I enter quadrant 3, right? Quadrant 3 down here, I'm still in the negative region. But the moment I get into quadrant 4, cos is positive again, because cos is the x-coordinate on the circle. Sine is the y-coordinate on the circle, which is why it goes positive, positive, and then negative, negative, differently than cos does, right? So I don't think that's, it's just something for you to help you understand, think ahead. For today, really, I just want you to make sure you understand this terminology and how we got these various answers and how to graph these things. One final point, just a lot of people when they do these graphs, they draw them really jagged, like straight up and down with sharp turns. I just want to point out that cos and sine do not have any sharp turns, right? Like it's like a gentle wave that's very circular, right? It does not like go up and then immediately turn in a jagged way, right? So I don't think I'm going to be collecting any graphs from you, except, well, yeah, no, never mind that. So when you're drawing, right, when you're drawing a sine graph, just make sure it's nice and rounded, okay? And that's it for today.